All right, chapter 5 then. Talking about, well, we've talked about now how we categorize matter super broadly. We broke that down into things that are, pure substances, which are elements and elements and compounds. We've also talked about mixtures of things. So you have homogeneous mixtures, heterogeneous mixtures. Today we're sort of diving farther down into the compound side, whereas last week we talked mostly about atoms, right? The structure of the individual atoms. This is going to be more about how those combine to make compounds. So, we're surrounded by compounds. We're surrounded by molecules. One of those molecules, though, it's table sugar, which is a molecule called sucrose. It's delicious. A sucrose molecule contains contains carbon, hydrogen, and oxygen atoms. But the properties of sucrose, the molecule, are very different from those of carbon, hydrogen, and oxygen. Right? Oxygen and hydrogen are both gases. Carbon actually has a ton of different forms as just pure carbon, but like graphite in a pencil or carbon nanotubes. Also, charcoal is made of carbon. Right, so by combining atoms together into compounds, we get very different properties from the elements themselves. These are the components of salt. This is sodium. Right? It's a softish metal. You can cut it with a butter knife, and it'll explode when you throw it in water. And then chlorine gas, which is incredibly toxic. But when you combine those together, you get table salt, which, just like sucrose, is delicious. So you get table salt with completely different properties from the elements that make it up. And the vast majority of compounds we encounter every day are actually compounds. Free atoms are very rare. They generally want to react to form different things. The noble gases are an exception to that, but they're also not super abundant in nature. So the compound is different from a mixture of elements. We've talked about this a little bit before because it's made up of atoms in specific proportions. So for water, there's always the one oxygen and the two hydrogens. It's always this 1-to-2 ratio. But in a mixture, like if you use, putting sugar into coffee, there's no set ratio for sugar and coffee. So if you had a balloon that had hydrogen and oxygen in it, they can be in various ratios. You can get like a scuba tank that has, different proportions of gas. We'll talk about it later, but for deep sea diving, you need to use heliox, which is helium and oxygen, rather than nitrogen and oxygen. Because if you go deep enough, again, we'll talk about it later, but the nitrogen becomes soluble in your blood and causes problems. So we can change these. We can change these mixtures up, right? So it doesn't matter. It's a mixture. It's hydrogen, oxygen, could be in any proportion. A water balloon, or a balloon full of water, has hydrogen and oxygen, but every one of those water molecules has 2 hydrogen atoms, 1 oxygen atom. And so it's always going to have the same amount or the same proportion of each. It was Joseph Proust who formally stated this idea that elements combine in fixed proportions to form compounds. Before that point, I didn't know, right? So it's like, what makes up pencil lead? How do you know that something is toxic or not? Aside from somebody eating it and they don't feel good or die. So this law of constant composition, though, which is an important concept to know, that all samples of a given compound have the same proportions of their constituent elements. You're probably going to get tired of me saying that over and over and over again. You probably already are. I'm tired of saying it. But it's very important because it's critical to chemistry. So we had an example similar to this in chapter 1, where we were looking at trends in data. that was water being split up into its constituent elements of hydrogen and oxygen. So if we did this with an 18-gram sample of water, you'd end up with 16 grams of oxygen and 2 grams of hydrogen. And when you divide those, you get the ratio between them. Now, it actually doesn't matter which way you divide this. It could be 2 divided by 16 or 16 divided by 2. The ratio then would just be upside down, and you'll get a decimal number. Normally, when you're trying to determine a ratio like this, you want to take the bigger number and put it on top and divide by the smaller number, because then you get whole numbers to work with. It's just a little easier to deal with. So you could take water from anywhere on Earth, do this experiment, and get the exact same ratio of 8:1 oxygen to hydrogen atoms, or mass of oxygen to hydrogen. So again, compounds have constant composition with respect to mass because they are composed of atoms in fixed ratios. And the mass of each of those atoms is the same. So if we have 2 samples of carbon monoxide obtained from different sources, and they're decomposed into their constituent elements, one sample produces 4.3 grams of oxygen and 3.2 grams of carbon, and the other sample produces 7.5 grams of oxygen and 5.6 grams of carbon. Are these results consistent with the law of constant composition? So how would we determine this?
Figure out the ratios for each.
Yeah, we can look at the ratio of each of these samples. Right, just like water, that ratio should be 8 no matter where you get the water. For carbon monoxide, it should be the same. So we can take our sample here of 4.3 grams of oxygen. And again, we're going to divide the larger number by the smaller number to give a whole number. So divide that by our 3.2 grams of carbon. And that will give us someday I'll remember to get this out beforehand. 4.3 divided by 3.2 will give us 1.34375 as our ratio of oxygen to carbon. This is our oxygen to carbon ratio. So then we do the same with our other sample. Color match these. So we'll have 7.5 grams of oxygen. We'll divide it by 5.6 grams of carbon to get, I didn't really leave enough space. So it'll be 1.3392, I'll just go that far, as a ratio of oxygen to carbon. So, are they the same? Yeah, they're close enough. And actually, if we use our sig figs, then the significant figures of our first answer is just 2 sig figs. So this will be 1.3. And then the sig figs of our second answer is the same, so 1.3. So those 2 numbers are the same. And even at, this whole number compared to this whole number, those are close enough, right? It's like a less than 1% difference between the 2. So those are both, or I guess they're consistent with the law of constant composition. So we've seen chemical formulas up till this point, but we haven't really talked about what they are. Our chemical formula indicates the elements present in a compound and the relative number of each of those elements. And we indicate that relative number by using subscripts, right? So the small number to the bottom right of that number, or of the letter or symbol. So for water, we have hydrogen and oxygen, and we know that we have 2 hydrogens because it has a 2 subscript to the bottom right. And then if there's a 1, we'd leave it off. It's implied. Right? We wouldn't write oxygen if there weren't any oxygens. And if there were more than 1 oxygen, we'd write that down with the appropriate number. So some common formulas. You probably see salt a lot. Sodium chloride, right? So sodium chlorine. It's table salt, and it's indicating that we have sodium and chlorine atoms in a 1-to-1 ratio. And so for every sodium, there's 1 chlorine. And this is different, that's a good point, this is different from the mass ratio because some atoms are bigger than others. I mean, just looking at the periodic table, you can imagine that hydrogen, which has a mass of about 1, has 1 proton and no neutrons, very different from the mass of chlorine, which has 17 protons, but also has 18 neutrons in at least one of its isotopes. So it has a mass of 35. So this is the atom ratio, not the mass ratio. For CO2 or carbon dioxide, we have carbon and oxygen atoms in a 1-to-2 ratio. So 1 being the carbon and the 2 being the oxygen. In something like table sugar, we have a lot more atoms, 12 carbons, 11 hydrogens, and 11 oxygens. So for table sugar, you'll always have that proportion of each of those elements. So we've talked about how elements are identified based on the number of protons that they have. Each compound is identified by the number and type of atoms that make it up. If you change that, you change the compound, and it's something completely different. So carbon monoxide is the chemical formula, or CO is the chemical formula for carbon monoxide. It's an air pollutant. It will also build up. This is why you shouldn't run your car in your garage with the garage door shut, because your car will produce carbon monoxide. And you should also not use gas burners to heat up your home in a closed space, because carbon monoxide will build up. But it's very similar to CO2, or carbon dioxide, which is the product of human respiration. There's also a joke where 2 chemists walk into a bar. The first one orders a water. He says, I'll have an H2O. Second chemist walks in and he says, I'll have an H2O too. He takes a drink and he dies, because H2O2 is hydrogen peroxide. Must have been a chemist bartender too. A very literal one. So changing these subscripts matters a lot and can have dire consequences. So the other thing we're going to talk about a lot in this chapter is just how to name compounds. And there are a lot of rules. And at the end of this chapter, there is a nice flowchart, which I think is also in the book. And I would keep that on hand for reference when you're working on the nomenclature worksheet, which is coming up. I think it's next week. So if we are naming or writing a chemical formula for something, we want to write the most metallic element first. And so this is why we had to talk about what are metals on the periodic table. And one of the trends is, as you go farther left on the periodic table, things get more metallic. The farther right you go, the less metallic they are. And this holds even for the nonmetals. So for sodium chloride, it's a fairly easy one. Sodium's on the far left, chlorine's on the far right. So sodium's more metallic, it goes first. For a compound with nonmetals, like dinitrogen oxide, nitrogen is to the left of oxygen. So it has, if only slightly, it has more metallic character than oxygen. And there is also a list here. So write the most metallic first, followed by the less metallic element. If you want something that's even more specific than that, you can use this order or this list here. One of the exceptions to this, which is a historical exception, is hydroxide. So the hydroxide ion, the oxygen gets written first, even though it's on the right side, and hydrogen's on the left side. But for everything else, we'll do carbon, phosphorus, nitrogen, hydrogen, sulfur, iodine, bromine, chlorine, oxygen, and fluorine in that order. So if you wanted to do an element that had hydrogen and sulfur in it, then it would be, well, H2S is hydrogen sulfide. So the hydrogen is farther left in this list, so it goes first. All right, so if we wanted to write some formulas for these compounds, we have a compound containing 2 silver atoms for every sulfur atom. Which element do we put first? Silver, thank you. Yeah, because silver is, well, a metal, right? We know that it is actually a metal, and sulfur is in the nonmetals. So then we have 2 silver atoms, so we'll have Ag2S. If we had, this was the example on the previous slide, but if we had nitrogen atoms, right, 2 nitrogen atoms, 1 oxygen atom, which of those goes first? Nitrogen goes first. So nitrogen is to the left of oxygen on the periodic table. So this will be N2O. And then if we had a compound with 2 iron atoms for every 3 oxygen atoms, which of these goes first? Iron. Whoops. So Fe2O3. This makes this look more complicated than it is. There's a lot going on there. We also have these things called polyatomic ions. If you want a list of polyatomic ions, there is one in the book. There's also the Polyatomic Ion Study Guide that has almost all of the polyatomic ions you're going to see in this class. So when we write a formula with a polyatomic ion, those polyatomic ions act as units. They're kind of treated like an element on their own, if that makes sense. They move together in groups. So when 2 or more of the same kind of polyatomic ion are present, we don't just increase the number of each of the elements or multiply it by the number of those groups. So let's say that we have this magnesium, and that's a nitrate group. You wouldn't write it, I'll do this in red. If we had 2 nitrates, write it like this. 2 nitrates and 1 magnesium. This would be a 2 plus charge. You would not write this as MgN2O6. You instead treat that as a single type of unit. So we'll put it in parentheses. Right, so not this. We'll put it in parentheses like this and put that 2 on the outside and to the bottom right. And then it's just like algebra where you multiply by everything inside the parentheses. So there are 2 nitrogen atoms, right? 1 nitrogen atom times 2. There's 3 oxygen atoms here, so it's 2 times 3 for a total of 6 oxygen atoms. So to highlight this point, we're going to count the number of each type of atom. So we have potassium, sulfur, oxygen. So how many potassiums do we have? 2. Sulfur? 1. And oxygen? 4. Easy enough. If we have the second compound, we have aluminum, sulfur, and oxygen. And how many aluminums?
2.
How many sulfurs?
3.
3 sulfurs. Because we have this subscript out here, and it's just outside of the parentheses, so we multiply everything inside by 3. So 3 sulfurs, and how many oxygens do we have? 12 oxygens. That can be easy to forget sometimes. It'll come up and be more important when we start balancing chemical reactions, chemical equations. Okay, so we've been talking about, up till this point, molecular formulas. And the molecular formula gives the actual number for that compound of each element. So this is the actual number of atoms of each element. The empirical formula is a little bit different because it's actually easier to determine an empirical formula than it is to determine a molecular formula. So the empirical formula is only the relative number of each type of atom. So it gives us the ratio, but it only gives us the simplest ratio between the atoms. So if we had something like, let's make up a compound here, N2O4, this would be, we'll say that this is the molecular formula. The empirical formula of that compound would be the simplest ratio between them. A little bit more room here. Would be NO2. And this would be the empirical formula. So it's much easier to break something down and then get the masses of each of the individual things and divide it. But when you do that, you just get this empirical formula. You got to do more experiments to get that molecular formula. So big difference being the empirical formula is not always the same as the molecular formula. The structural formula gives us even more information than the molecular formula. So remember glucose or sucrose is C12H22O11. Actually, do not remember the structure of sucrose, so I'm not going to attempt to draw it out. But you can imagine that there's a lot of ways to arrange those atoms. That there's only one correct way to arrange them to make sucrose. So the structural formula tells us how many of each atom there are. It's the actual number of atoms, just like the molecular formula. But it also shows you how they're all connected. So for these are really different types of structural formulas or ways to do a structural structural formula. We have molecular models. So they're three-dimensional representations, so kind of even taking that structural a step further, how they look like in 3D space. Ball and stick model is as simple as it gets. These are generally the colors that are used for each element. But there are also space-filling models that represents how close the atoms actually are to each other and how much space they take up. When I talk about how much space they take up, it's their electron cloud, because again, the nucleus is tiny. So here's a molecular formula for methane. Right? Just tells us that there's 1 carbon and 4 hydrogens. The structural formula shows us that all of the hydrogens are connected to the carbon in the middle. Right? So you wouldn't write this as like H, C, H, H. Would be another theoretical way that you could combine those. The ball and stick model shows us that it's not just an X or a plus sign. They're actually in 3D space more like a tripod. So there's 3 sticking out as that tripod on the bottom, and then there's 1 that comes out on the top. So these formulas are useful for different types of things and conceptualizing or thinking about different concepts. Right? For most of the stuff, you're going to be able to use the molecular formula in a chemical reaction. You don't need to know anything necessarily about the structure or the space filling or the 3D shape. If you go into organic chemistry, that becomes a lot more important. So macroscopic world, that's the level that we exist at, that we interact with things at. If you look at water, it's wet. You know, it looks like water. As you move down, there's this atomic and molecular world where it's helpful to think of things conceptually. So you can understand better how water behaves and why it behaves the way it does. If you think about it as these little tiny, I don't know what to call them, almost like Mickey Mouse heads floating around, because that determines the way that they interact. The symbolic way is the most useful for conveying something to somebody else. to write it in a paper, or to do chemical equations and write out chemical reactions. So you need to sort of understand all of these different levels to have a full understanding of the chemistry. This is not the flowchart that I was talking about for the lists, but this sort of elaborates on what I was talking about earlier. So we talked about pure substances. We talked about elements, right, being made from a single type of atom from the periodic table. We talked about compounds being made up of multiple atoms in a specific proportion. So now we're going to talk about, first, atomic and molecular elements. So again, just a single type of atom. And then we're going to talk after that about molecular and ionic compounds. So two different ways that different types of atoms bind together. The atomic elements are the ones that exist in nature with single atoms as their basic units. Metals are a great example of this. They sort of, on an individual level, exist as the metal itself. Molecular elements is a special set of the elements, these guys here. So you can use a couple different acronyms to help remember them. The one that I always remember is Brinkelhoff, because it's a funny name. So it's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. And so instead of being individual elements in nature, they bind, they follow the buddy system, and they find another element, another of the same type of element. Right? So nitrogen binds to another nitrogen. Right? So if we had a nitrogen, it would be bound to another nitrogen. So those are the molecular elements. So if you identify, or if you're trying to identify what something is, you can say, all right, is it made of one type of atom? Okay, yes, it's an element. Is it one of these? If it's not, then it's an atomic element. If it is one of this on this list, then it's a molecular element. You'll always have a periodic table available to you on exams and stuff. So there's a way on the periodic table. Oh, wait. Got ahead of myself by one slide. This is what I was talking about with metals. Right? They're existing as the single mercury atoms here. You could go ahead and cut those and split those apart. They're not bound together like in a compound. The atoms of chlorine, on the other hand, are bound together in these diatoms, so two atoms. So in the periodic table, there is hydrogen, which is out by itself. But then starting with nitrogen, going over to fluorine, and then all of the halogens except for, I think it's astatine at the very end, those are your diatomic elements, or molecular elements. For me, patterns on the periodic table help a lot. So this L shape. And they're all gases. Right, so you could think about this as carbon's not a gas, because carbon makes up graphite, charcoal. So nitrogen, through all these gases, are the molecular elements. The other acronym commonly used is horses need oats for clear brown eyes, but not EYES, but the letter I. All right, so that's elements. We've got two types of elements. Compounds, we have molecular compounds. And the key for molecular compounds is they're made of two or more nonmetals. In the ionic compounds, well, they usually contain a metal. Usually here is really almost always. They have cations paired with anions, usually contain a metal. Ammonium, NH4+, is an exception to that. So here we have sodium chloride, where we've got sodiums and chlorine, and then something like carbon dioxide. And on an atomic level, the big distinction between these two is that carbon dioxide molecules exist as individual molecules. In an ionic compound, it's more of a lattice or like a matrix of alternating sodium and chlorine and sodium chloride, or alternating ions in ionic compounds. So we talk about those as the simplest unit and the simplest ratio of those ions. In this case, sodium and chlorine, when in reality it exists as a big crystal of sodium and chlorine. Oh, it was ionic compounds was the next slide. Okay. So will be composed of a metal and a nonmetal. So you can make a series of sort of logical checks for is it one thing or is it the other thing. If it has a metal in it and it's composed of two different types of atoms, then it's an ionic compound. And so this sort of most basic unit that I was talking about is called a formula unit. So for sodium chloride, that's the simplest unit. But kind of like building something out of all the same type of Lego brick, these are actually in a three-dimensional alternating matrix of sodium and chlorine. So think of a wall or a block or something made of these individual pieces, all stuck together. All right, so we can kind of build a tree now, our own little tree, and with questions that we can ask and answer about each compound or element that we encounter to organize them into these different categories. So if we're starting out, we want to know, is it one type of atom or is it multiple types of atoms? All right, and we can really just ask one question. Are there more than one, I'll say, type of element? All right, so if we have more than one type of element, then it can't be, well, just an element, right? It can't be a pure substance. So if the answer is yes, then we're going to have a compound of some kind. If the answer is no, then we're going to have a pure substance. So for chlorine, do we have more than one type of element? Nope. So we're going to say no, it's a pure substance. And we have two different types of pure substances. And we can ask one question to see if they are a atomic element or a molecular element, molecular element. And that, is it one of the Brinkelhoff? And yes, right? Chlorine is the coal in Brinkelhoff. So if the answer is yes, then it's a molecular element. If the answer had been no, then we'd have an atomic element. All right. Moving on then, if we have nitrogen, oxygen, is there more than one type of element? Yes. And we have two different types of, I keep writing these in, but I need to write the question first. We have two types of compounds that we know about at this point at least. Right, it can be a ionic compound or it can be a molecular compound. And I think the easiest question to ask is there a metal? No. Right. In this case, no. So if there's no metal, then what is it? Molecular element. Or not molecular element, excuse me. Molecular compound. If the answer had been yes, then we'd have an ionic compound. For a lot of these categories that we've been creating, there are distinct properties between the things, right? So you can ask a question, does it have one of those properties? If it's yes or no, then you can sort them out. So one study tip that I have is to make flowcharts like this, where you can ask questions and then sort things that way. It does a couple things, is it gives it a structure in your mind, but it also means that you have to have an understanding of what those separating properties are in order to make the flowchart in the first place. So you really got to think through each of the categories and say, well, how is a compound different from a pure substance? All right, so for gold, is there more than one type of element? No. Is it a Brinkelhoff? No, it's atomic. This was molecular compound. I'm going to abbreviate that, and this was a molecular element. Sodium oxide. More than one type of element? Yes. Is there a metal? Yes. Sodium is a metal. So remember on these periodic tables, anything to the left of the zigzaggy line is a metal. So we do have a metal. So this one is an ionic compound. How about for E? More than one type of element? Yes. Is there a metal? Yes. Yeah. Chromium is a metal, so it's also ionic. This is going to be very important, being able to identify these things, because they're named differently. This comes back to something for the element quiz this week, right, where you have to know the charges. We have a lot of elements with predictable charges. So metals in 1A, 2A, or 3A have a 3+ charge. So right, starting on the left, group 1, that's 1A. Group 2, which is the second column, that's 2A. Those are all 2+ charges. Then this periodic table doesn't have the group numberings, but 13 is 3A. So boron, well, boron kind of, but boron, aluminum, gallium, and indium all have 3+ charges. So the reason that the elements are on the list, are on the study guide for Element Quiz 2, I chose those elements because they're all the predictable charges that you'll need to know for this class. There are a couple other ones that aren't so easily identified with a column. That's zinc and silver. So zinc and silver, zinc has a 2+, and actually cadmium also has a 2+ predictable charge. And then silver is 1+. So that forms like a little triangle. I'll draw it on here. It's aluminum, gallium, indium, then there's cadmium, zinc, and silver. So these form a triangle periodic table. Like I said, patterns, shapes help me remember things. So I just remember that in that little triangle, it's 3 on the right, 2, and then 1. And there's 3 elements, 2 elements, 1 element. The only one that's not on there, or the only one that's not in here, is scandium on the far left. Actually has a predictable charge of 2+. Okay. Right, this gets back to writing formulas for ionic compounds. So every ionic compound has a positive and a negative ion. As we talked about, there are cations. Excuse me, Mr. Calculator. Cations and anions. And the important thing to remember is that the charges always add up to 0. So if you had a compound formed of, let's just use zinc, 2+ charge, right, that's a predictable charge. We haven't gotten to the anions with predictable charges, but let's use fluorine, which has a predictable 1- charge. So zinc is 2+, or yeah, let's write it as a +2. So our +2 plus a -1 doesn't equal 0. So we need to add another fluorine, because we can't have half of a zinc. We can have one more fluorine. So if we say that there's 2 fluorines, this will be now a -2 charge. So this will be 0. So the correct formula for zinc fluoride would be ZnF2. And that holds true for all the ionic compounds. The positive and the negative charges equal 0.
So for ionic compounds, charges always add up to 0?
Yeah. So when you're writing a formula for an ionic compound, right, this is going from the name to the formula, write the symbol for both ions, including the charges, and then make the magnitude of the charge. Oh, this is the crisscross method. Yes. Let's do picking. I think this is one of those things that I feel like is better with a good example. So let's do zinc again. So let's say we've got zinc phosphide. We want to write the formula for this. So we want to first write the symbol for both ions, including charges. So zinc is a 2+. Phosphine, phosphide is the ion of phosphine. It's going to be a P3-. So we want to make the magnitude of the charge on each ion become the subscript for the other ion. So the magnitude of the charge on zinc is 2. It's 2+. We ignore the sign, we just take the 2. So when we have our formula, that'll be ZnP. We take this 2, and we make it the subscript for P. So it'll be a 2. Then we take the magnitude of the charge for phosphorus. Here's a 3. And we're going to make that the subscript for zinc. So this will be a 3. And there will be some cases where you need to reduce the subscripts to give a ratio with the smallest whole numbers. I feel like people forget this one a lot. So if you ended up with, talked about earlier, it's not an ionic compound, but, or I can do an ionic compound. If you had vanadium oxide, V2O4, you would simplify this to VO2. If after the crisscross method you got V2O4. And you want to check to make sure that the sum of the charges of the cations, so it's the one with the positive charge, is exactly cancels the sum of the charges of the anions, right? So it's equals 0. So we have 3 zinc ions, and they have a +2 charge each. So it's going to be a +6. And then we have 2 phosphorus times a -3 charge. So that'll be -6. So we add those up together, we get 0. So we know that this ionic compound has to be 3 zincs and 2 phosphorus because that adds up to 0.
Oh, I see what I did. Because I was thinking just to add the 2 into the zinc, but
Oh.
make it into a 4, right?
Multiply it, yeah. Yeah. So you're multiplying the number here by its charge. Questions? Okay. You can ask a question now, or you can ask a question later. It's fine. Okay. So let's write a formula the compound that formed from strontium and chlorine. So again, we want to write out the symbols for each. Strontium is Sr, and it's in column 2A. So what charge does strontium have? 2 plus. And then chlorine is in 7A, which we'll get to how to memorize those, but it's a 1 minus charge. So we can use the crisscross method for this. There's really two ways. You use the crisscross method, or if it makes sense to you and more intuitively, you can just add the appropriate number of chlorines to cancel out the charge on strontium. But using the crisscross method, you say 2, we're going to move the magnitude of that, right, so without its symbol, over to chlorine. And then this is a 1 minus charge. So we're going to move that 1 without the symbol over for strontium. Now, because it's a 1, we're going to leave it off because that's implied. Oh, cool. Decline. Second one today. So when we do that, we'll get strontium with a 1, but it's implied, Cl2. And if we wanted to check to make sure that our charges match, that they add up to 0, maybe if I write it this way, it'll help. So strontium has a 2 plus charge. So there's 1 strontium atom times the charge of 2 plus, which equals 2. And then for chlorine, which has a 1 minus charge, we have 2 chlorine atoms. So we'll have 2 chlorine atoms times the charge of 1 minus for a negative 2. And so those will add up to 0. So it's properly balanced. If you want to know a deeper explanation of why they bond this way, I can do that for you later. Sometimes it helps to understand that first. But this is the sort of shorthand, quick way to figure out how these combine. So we're going to write a formula for the compound that forms from aluminum and nitrogen. So aluminum is in the 3A column. It's also the tip of that triangle that I was talking about. So there's a 3 plus charge. And nitrogen is in 5A. I think we're going to get to those on the next slide. But for the negative charges, it's like 7A. You just take its column number, which would be 7, not 17, minus 8, and that'll give you the charge. Then for 6A, which is also 16, you do 6 minus 8, and those are 2 minus charge. And then for column 15, it's 5 minus 8 for 3 minus charge. So nitrogen is a 3 minus. So we can use the crisscross method here. We can say, take the 3, make it the subscript of N. Take the 3 from the 3 minus, make it the subscript for aluminum. So we get Al3, N3. But this is not the simplest ratio. So at this point, you can divide these to get the simplest ratio. This one's fairly easy because they're both 3. So we can divide by 3 and get AlN. Because even though these charges balance, again, remember, these are ionic compounds. So we want the formula unit. We want just the smallest piece that makes up the whole lattice. So this is 3 of those pieces together. We can simplify that to just 1. And then if we have aluminum, if we want to check our charges, this is a 3 plus, and our nitrogen with a 3 minus. For aluminum, we have just 1 atom times a 3 plus charge. And then we have 1 nitrogen times the 3 minus charge, which I'm saying 3 plus and 3 minus because when we talk about charges, that's the way they should be written. But it's the same as a positive 3 and a negative 3. So this is a 3, and this is a negative 3. So when we add those together, get 0. Is there any questions? No? Okay. This table is intimidating. There's a lot to memorize here. These are the polyatomic ions in the table that I alluded to earlier that is in your book. These are not laid out. These are laid out in alphabetical order? No. They're kind of laid out in alphabetical. But these are not really organized in any sort of way. The study guide has actually some rules on there for how to remember the systematic names of a lot of these. And they're sorted into their element groups. So you can memorize these or look them up. I'm expecting you to memorize them. That's why there's a quiz on it. So I can give you points for memorizing them, in addition to how they'll help you on exams. I guess there's not a slide that explains this explicitly. These also form ionic compounds. So again, you'll have a metal and a polyatomic ion. And works the same way. Each of these ions has, zoom this in, so like acetate, that entire unit has a 1 minus charge. And the entire unit for carbonate has a 2 minus charge. So you got to treat that group together with that charge. So if we wanted to form a compound between calcium and nitrate, again, we just write out calcium and nitrate, which at this point you go look up. These won't be prevalent on the first exam because this is chapter 5, so that would be exam 2. So don't worry about memorizing these for next week for the exam.
Does that mean the exam's only chapters 1 through 4?
Yeah, the exam is chapters 1 through 4. So we have calcium and then nitrate, which you can go look up on a table, but it's NO3 minus. Then calcium is in group 2A, yeah, so it has a 2 plus charge. So we can use the crisscross method here again. We say that we're going to take this 2, we're going to make this a subscript of 3. Or sorry, not subscript of 3. NO3, nitrate. We'll take the 1 and make that the subscript of calcium. And then if you remember, when we add a subscript to a polyatomic ion, we need to use parentheses to show that we have multiples of that group. So this is NO3, and then 2 of those. So if we want, we can check the charges also. Calcium 2 plus, there's 1 of those times the 2 plus charge. And then nitrate, we have 2 nitrates, and 2 nitrates times a 1 minus charge. This is going to be 2 and a negative 2, 0. So for these ones, I think it's easy enough to say that, calcium has a 2 plus charge, nitrate has a 1 minus charge. We're going to need 2 nitrates to cancel out the 2 charge on the calcium. The crisscross method is especially helpful for when you have weird multiples. So if you had I think chromium has a 7 plus charge as one of its possible charges. So you had chromium and say nitrogen, which has a 3 minus. Then what is the least common denominator or the least common multiple of those 2 numbers? Well, the easiest way to do it is just say, I'm going to take 7, put it over here, and take 3, put it over here. So it would be CR3 and 7. rather than trying to think about how to combine those. So if we had aluminum and phosphate, this is sort of an example of one of these. So symbol for aluminum, the symbol for phosphate is PO4, and it has a 3- charge. And then aluminum is in group 3A. Again, it's part of that triangle. Has a 3+ charge. Oh wait, no, I was thinking of something else. So again, we can use the crisscross method here. Or we can say that, well, aluminum has a 3+ charge and phosphate has a 3- charge. Those are already going to cancel each other out. So we're going to get aluminum PO4. Because if we do the crisscross method, and this is not, I'm not saying it's wrong to do the crisscross method. If the crisscross method makes sense, use it every time. It'll work. But there are shortcuts that you can take. So now we're going to do the crisscross here. So we'll have aluminum 3, PO4, and again, because this is a polyatomic ion, add parentheses, and 3. But again, we've ended up with 3 of each, and we can simplify that. So if we divide both by 3, we have Al, PO4. And then again, because aluminum has a 3+ charge, we have 1 aluminum times that 3+. We have phosphate with a 3- charge. We have 1 phosphate times that 3-. So we get 3, -3. If we add those together, we get 0. So ultimately, what you're doing is balancing the charges. An easier way to do that sometimes is the crisscross method. Sodium sulfite. So we have sodium. The sulfite ion is SO3, 2-. And then sodium is in the 1A column. So it has a 1+ charge. So we can use the crisscross again and say that 2, right, is the magnitude of sulfite's charge. 1 is the magnitude of sodium's charge. So we're going to Na2, SO3. And you could go and check the charges if you wanted. So nomenclature is the systematic rules, or is the set of rules that we use to name things. And it's systematic in that everything that has similar properties gets named the same. So instead of things like water and ammonia and ammonium, common names for certain things, we instead come up with sort of standard names so that anybody knowing these rules could name something or derive from that name the compound that it's describing. So again, like I mentioned before, there are different naming systems for different types of compounds. So elements are the easiest, and diatomic elements are also very easy because they're just the element name. But if we have ionic compounds or molecular compounds, those are named differently. Right, so common names like water and ammonia, their name is historical, has nothing to do really with the actual molecule. The nomenclature systematic names are derived from the molecule. So if we're going to name ionic compounds, first you have to identify it. So you can use the flowchart that I put up there before. There's one at the end of this chapter as well. The simple rule, though, being if you have a metal and one or more nonmetals, it's ionic. And then you'll learn this, that in chemistry, there's an exception to everything. So the exception to this is ammonium. If you have ammonium and one or more other nonmetals, it's ionic. The rest of the time, metals. Metals make ions, or metals make ionic compounds, but also ammonium.
Can you repeat that, please?
So if it has a metal and one or more nonmetals, it's ionic. And if it's ammonium, so this NH4 plus, and one or more nonmetals, then it's also ionic. So if it's a metal or ammonium. All right, a metal or ammonium, and one or more nonmetals. So metal and nonmetal, and ammonium, those are ionic compounds. And then inside of that, and this is another reason that element quiz 2 is so important, is that there are metals that form one type of ion. Those are the ones that are on the element quiz, the ones with predictable charges that we've talked about today. And then all of the other metals which form more than one type of ion. They're named differently. Slightly differently, but they're named differently. So these are, this is another table of those elements. So we talked about 1A and 2A and how those are 1 plus and 2 plus, respectively. There's also aluminum, gallium, and indium. But I've also mentioned that zinc, cadmium are 2 plus, and then silver is 1 plus. And then we also have these negative charges over here that are predictable. But for naming ionic compounds, oh sorry, I forgot about scandium, which is 2 plus. These are the predictable cations. So if it's one of those, use rules for predictable cations, which we'll get to. If it's not, then you use the other rule or naming scheme. It's just another periodic table with just the metals on it rather than having the nonmetals. So first talk about what if it's not one of those? If it forms more than one type of cation, then we need to indicate in the name what the charge is. Because remember, if we have an ionic compound, the combination of the metal and the nonmetal is dependent on the charges, because they have to add to 0. So if you have a compound with iron 2, we'll just use iron chloride, so it'd be FeCl2. But if you have iron 3, this would be FeCl3, because each of those chlorines has a 1 minus charge. So you'd get a different compound. So you can't just write iron chloride. You have to indicate what the charge is, because it could be multiple compounds. So we use Roman numerals for those and indicate in parentheses like this what that charge is. There are some historical names, and we're not going to use them because they're more confusing than writing the Roman numeral. These are the older names. I'm not going to use them because why not just write chromium 2? Or, I mean, why write chromium 2? I mean, why write chromus, instead of chromium 2? I don't know. For me, it's way clearer. These are hard to remember because chromus is 2 here, but cuprous is 1, and stannous is 2, and mercurous is 1, and so it could be 1 or 2. Don't use those. On the nomenclature worksheet, I will know if you Googled it if you write stannous or stannic or ferrous or ferric. It'll be a dead giveaway. So we're going to use these instead, though, where we have the name of the element and the charge in Roman numerals. For anions, they all, in ionic compounds, have the same rules. For the monoatomic anions, not talking about polyatomic ions here. You take the ending of the nonmetal, so fluorine, and you change it to IDE, so fluoride. Chloride, bromide, iodide, oxide, sulfide, nitride. Just change the ending to IDE. So the IDE form is the ion. The other one, which are mostly INE, right, is the element, not the ion. So all of the ionic compounds we'll encounter are just two ions, a cation and an anion. Won't get any more complicated than that. The name of an ionic compound is the name of the cation, followed by the name of the anion. The cation is usually the first element, where the exception is ammonium. Because ammonium's weird. I'm not going to use that very often in examples, if ever. And then the anion is everything after the metal. So for the compound, KBr, right, we have potassium. Now, is potassium one of the predictable charges? It is one of the predictable charges. So all of the cations in 1 and 2 and 3, and then the select other few. So we do not put the charge of potassium because it's always 1+. We don't need to write it in. And then we change bromine to bromide. All right, for this next compound, we have zinc. Is zinc one of our predictable charges? It is. It's one of the select others in the triangle of silver, zinc, cadmium, aluminum, gallium, indium. So because it's predictable, we don't have to write the charge. And we do not need to indicate how many zincs there are in this compound, because the charge is always the same. The charge of nitrogen is always the same. So this is zinc nitride. And from that name, we would get this every time. Right, we would be able to derive the formula from the name based on the charges of zinc and nitrogen, because they always have to add up to 0, and the charges are always the same. Shoot. 623. Well, we'll go over this, but I think we'll recap it on Thursday too. So if the metal forms in one type of ion, if it isn't one of the ones that we've talked about, you can determine the charge based on the chemical formula of the compound. And so what you do is you determine the charge on the anion first. We know that the sum of all the charges has to equal 0, so it has to be whatever charges will be canceled out or will cancel out the charge of the anion. So for iron 2, or for iron oxide, we can figure out that oxygen here, or we know that oxygen has a 2- charge. We know that there's 3 oxygens, so 3 times 2, so it's oxygen 2-, like I was doing before. So 3 oxygen atoms times its charge of 2- means -6. So then for iron, we don't know what the charge is, but we know that we have, in this formula, 2 iron times some unknown charge. Right? This is what we don't know, but it has to cancel out that -6. So it has to be a +6. So then 6 divided by the 2, right, divide both sides by 2, means that our charge on iron is equal to 3+. That's why the charges adding up to 0 is critical. Okay. we're going to be changing the ending of the monoatomic ions, so the ones that are made up of a single type of atom, they'll be change the ending to IDE. So it's okay if there's more than one oxygen, right? If there's two oxygen there, it's still one type of atom, so it's still oxide. If you wanted to figure this out using that formula, right, we could say that this plus this charge has to equal 0. We could say that X and 1X, because we have one lead, plus one oxygen atom with a 2- charge has to equal 0. So then X plus -2 equals 0. X equals +2. So you add 2 to both sides. So then for copper sulfide, again, checking if the metal is on one of the metals that is a constant charge or consistent charge. It's not. It's over there above gold, or above silver and gold. So we're going to need to determine what the charge is on that copper. So we're going to have copper, and we're going to have 2 of those copper atoms. Maybe it's easier to think about if you write it out like this, right? So 2 coppers, each with a charge that we don't know. And then we have 1 sulfur atom with a 2- charge. So if our sulfur has a 2- charge, then what does each of these has to be to balance it out?
1+.
Yeah, 1+. All right, because 1 + 1 will give us +2, which is the same charge, same magnitude, opposite charge of the sulfur. So the name for this one is going to be copper 1 sulfide.
Which ones are the ones that normally have a stable one or a constant?
The constant charge are the ones that were for this quiz.
Okay.
So group 1 and 2 are going to have 1+ charges and 2+ charges respectively. Scandium has a 3+ charge. Aluminum, gallium, and indium all have 3+ charges. So they're all on top of each other. There's 3 of them. Then zinc and cadmium both have 2+ charges. And then silver has a 1+ charge. So it makes this staircase or small pyramid. Cadmium, right? Yeah. Yeah, so it's 3+, 2+, 1+. So those are all of the metals that we have that form consistent charges, or always form the same charge. So oxyanions, we're talking about, I was just mentioning monoatomic ions. So you can use oxygen, fluorine, they're usually always nonmetals. So if you have just one of those types of atoms, that's a monoatomic ion, monoatomic anion. But we also have polyatomic anions. And one of the special groups are oxyanions. There are a lot of oxyanions, but they are named systematically. So using that systematic name is the best way to memorize them. Actually, I'll flip over to this real quick, because on here, for the Polyatomic Ion Study Guide, this has all of the oxyanions, and then a lot of the other polyatomic anions that you're going to need to know. So this will be another one of these element quizzes in 2 weeks, right, after the exam. And the rules actually that we're going to cover now are on this as well. And so I recommend memorize these rules, and then it'll make memorizing all of this a lot easier, because you need to remember like 8, 9 of the base forms, rather than all, ends up being more than 3 times that, 4 times that. So The oxyanions contain different numbers of oxygen atoms for each series. So a series being the oxyanions made up of nitrogen or oxyanions made up of sulfur. They'll have one element. Cool. Is it back? Okay. So you have oxyanions made up of one element followed by oxygen. And then different numbers of oxygens, which are determined or which are related to the name that it has. So you can treat the ones with endings of ATE as the base form. Some of those have 3 oxygens, some of those have 4 oxygens, but then the rules for more or less oxygens in that same series is based on the name. So nitrate is one of the ones with 3 oxygens. If you change that to ITE, that's the light form, nitrite, and that has 1 fewer oxygen, but the charge remains the same. So for each oxy anion series, they all have the same charge, just different numbers of oxygens. Then for sulfate, the base form, the ATE form, has 4 oxygens. And if we take 1 oxygen off, then it's the ITE form with 3 oxygens. But it still has a 2- charge. A lot of them have more than just the 2, and actually even those have more than 2 in the series. But there are 2 other names that we use, or 2 other prefixes or suffixes that we use. So there's hypo. So the hypo, it'll be hypo and then have an ending of ITE. That means we've taken 2 oxygens off of the base form. So for chlorate is the base form, which is ClO3-. Chlorite, right, ITE, that's taking 1 oxygen off. So it's now ClO2. And then if we do hypochlorite, then it's 2 oxygens less than the base form. But they all have the same charge. You can go the other way 1 step. If you start with the ATE form, add per to the front. So this will be per and then ATE at the end. That adds 1 more oxygen, but again has the same charge. So I definitely recommend memorize these, the base forms with ATE, and then if you know that per adds 1 oxygen, ite takes off 1 oxygen, and hypoite takes off 2, you can figure out all of the rest of them. The back half, these last few slides are going to feel like a lot, because they are a lot. So polyatomic ions are used a ton in just like everyday life. Sodium hypochlorite is a household bleach, right? So it can destroy color, although there is color-safe bleach, and it'll kill bacteria. Sodium bicarbonate is baking soda, which creates carbon dioxide so that your baked goods will rise. You also have calcium carbonate, which is the antacid in Tums and Alka-Mints or Alka-Seltzer. And then sodium nitrite is actually a preservative that's not used very much anymore in meats because they've done some research and it's not very good for you. Which, go figure, it's a preservative. So for ionic compounds, we still name them mostly the same as we do other ionic compounds with monoatomic anions. But now we just use the name of the polyatomic anion or the oxy anion at the end. So this is manganese. So we got Mn. And again, checking on the periodic table, manganese is not one of our consistent charges. So it can form, I think, 2+, 4+, 5+, and 7+, maybe 6. It can form several different charges. It makes a nice purple color. So this will be manganese. and then we need to determine what that charge is. So we could write it out like this, and we say MnX, and then we'll still use our anion, in this case an Oxy Anion, to determine what that charge on manganese actually is. So this is where memorizing these comes in handy. All of the nitrate series Oxy Anions, so for each of these anions, they're going to have a 1- charge. And then we have 2 of them, right? So then our charge on manganese should be 2+. Because we have the 1-, the 1-, so this has to be the opposite of that, right? So together, these would be 2-. So this must be 2+. So manganese 2, and then this is nitrite, because the base form for the nitrogen series has 3 oxygens. So nitrate is NO3-. Sorry, should be more consistent with these. Nitrite. Nitrite. All right, so for this next one, what's our first element here? Cobalt. Used in a lot of electronics, especially in touch screens. So cobalt is, again, an element or a metal that does not form a consistent charge. So we'll have to determine what that is. And again, just like with manganese nitride or with the other ionic compounds, we can do that using our anion, because anions are really consistent with the charges that they form. So here we have cobalt with some unknown charge, and then we just have one. This is carbonate. So this is the ATE form of the carbon series of oxyanions, and it has a 2- charge. So then our charge on cobalt is just going to be the opposite of that. It'll be a 2+. And then we'll just write carbonate. So it could be easy to confuse this with, well, the reason that it has to have a different ending is because you don't want to confuse it with cobalt carbide. So that would be, actually carbon usually forms, if it does form a charge, usually it forms a positive charge, but we'll just say it forms a negative charge of 4-. So this would be cobalt carbide. So it's the ending that tells us what it is exactly, and the first part tells you really what the element is. Right? So the carb, you would know it's carbon, but because it's not carbonate or carbonite, then it has to be the element, just the element carbon. Any questions on the polyatomic ions?
So carbonite is real?
Carbide?
Carbonite?
Carbonite is real. Yeah. Carbonite is real. It's not something that you could freeze somebody in, though. Okay, so that was the end of the ionic compounds. So we've got several types of ionic compounds. There's ionic compounds with metals that form the same charge every time, right? A consistent charge. Those are the ones that were on here, the element quiz. There are also those that form multiple charges, and then also using monoatomic ions versus using polyatomic ions. Again, there's a flow chart at the end of this that's very helpful for that. For molecular compounds, I feel like molecular compounds, in my mind, are easier because we have prefixes that correspond to different numbers, and then we use the name of the first element and the base name of the second element plus IDE, just like we saw with cobalt carbide. We change that ending to IDE. And for these, we're just going to learn binary molecular compounds. Oh, right, and these are to be super clear here, these are two or more nonmetals. So ionic compounds have metals. Molecular compounds are just nonmetals. So these are the prefixes that we use. Mono for one, di for two. Some of these, I think di makes sense. Tri is like a tricycle. Tetra is the one that I don't really have a good corollary for. It doesn't get used very often. But if it helps, you can think of the two T's. You need the 4 lines for the two T's, and that's tetra is 4. Penta is like a pentagon or a pentagram. Hexa, like a hex wrench, which might not be familiar to everybody, huh? Or a hexagon, yeah. Hepta is like a heptagon. Octa is what stop signs are, octagons. Nona is 9, that one kind of sounds like 9, and deca is 10. So if you can come up with ways to remember those, or again, you get was it this class? No, it was yesterday's class. I just want to be clear about the 3x5 card, 3-inch by 5-inch card. You get a single one of those. There's some confusion. I think it was at my Reedley College class for some people that they thought they could have a stack of 3x5 cards. You get one, front and back, and then I'll collect them at the end. So if you want to take a picture of it or copy it for yourself, you can do that. So to make sure that you're not cheating somehow. So if there's only one atom, molecular compounds. This is like a rule. There's a lot of these normally things, right? Like how we leave off ones. If there's a single element, right, we don't put a 1 here for carbon and carbon dioxide. We also wouldn't put mono if there's 1 carbon and it's the first element. So this would be just carbon, and then di meaning 2, ox indicating that it's oxygen, and then ide, which indicates that it's an ion. So the full name would just be carbon dioxide. Versus if you had a case of where we do use mono, carbon monoxide. Write that out. Right, so we don't write monooxide, it's just monoxide. Similarly with this dinitrogen, so write 2 nitrogens. We do say mono, but we leave off the extra O, one of the extra O's. It's not monoxide. So you want somebody to say monoxide. So sometimes that first vowel is dropped. This is not a thing that I'm going to be a stickler on in terms of spelling things. Right? If you got the idea that it's mono or one of the other prefixes and you don't drop an extra vowel in there, that's okay. That's something that kind of comes with practice. So for this compound, we have nitrogen and oxygen. What would be the prefix for nitrogen? Di. So dinitrogen. And then for oxygen, tetraoxide. And this is one where you might write tetroxide, but again, not going to be a stickler on it. For this next compound, and that's it. This is how you name them all. Proper prefixes, change the second one to IDE. So you have a single nitrogen. So we generally leave off the mono because it's the first element. And then what prefix would we use for hydrogen? Yep, tri, and then this one is hydride. Hydrogen becomes hydride as the ion. So just to give you a little bit of the why we have to put these numbers in front, because we don't have charges that are consistent. Well, these aren't ionic compounds. So they're not bound together based on the charges that they have. They're called covalent bonds, It's a little more murky than that. So there's no way to predict from just a name, like, for example, nitrogen hydride. There's no way for us to predict from just this name how many of each element there would be. Whereas for ionic compounds, we can use the charges of one of them, or both of them if given, and figure out how many of each element there will be in the compound. So don't use these prefixes on ionic compounds, or don't use these prefixes when there's metals present. So our acids now, that was it. So basically we did, in this chapter, like 5 or 6 slides for molecular compounds, and then there were like 40 slides for ionic compounds. And we just have really fewer than 10 slides here for our acids. So we have 2 types of acids that we're going to learn how to name. Binary acids, which, as the name suggests, are formed of 2 different types of elements. And it'll be hydrogen and a nonmetal. The oxyacids, as you might guess, are formed from the Oxy Anions and hydrogen. So it'll be hydrogen first, a nonmetal, and then oxygen. And for any of these acids, hydrogen is going to be the first element. So if you're trying to identify a compound, you can really look at the first element. If it's a metal, then it's ionic. If it's a nonmetal, well, a nonmetal except hydrogen, it's a molecular. If it's hydrogen, it's an acid. You got to make some more determinations from there, but those are like our 3 broad categories of naming, and then each of those breaks up into, I guess the metals and the acids break up into a couple more categories. So binary acids, you start with identifying that there's a hydrogen first, and that there's only one type of nonmetal second, so exactly 2 elements. And then, that's right, these are hard to read. Hydro is the prefix for binary acids. Then it's the base name of the nonmetal plus IC. It's like we changed monoatomic ions to IDE. We changed them for acids to IC. So HCl becomes hydrochloric acid. For HBr, hydro again, bromic acid. And it's this hydro in front that tells us that it's a binary acid. So if you're working the other way. So here we can identify that for HF, we start with hydrogen. So we know it's going to be an acid. We say that we only have one other element, so it's going to be a binary acid. Then the first thing we can write, because all binary acids start with hydro, but hydro, then the base name of the second element, so this will be fluorine, and we change the ending to IC and add acid at the end. So we got the prefix, suffix, and then an acid at the end. For this next one again, first element's hydrogen. So it's whether it's one hydrogen or multiple hydrogens. We have hydrogen first, and then only one other type of element, selenium. So again, it's hydro, selenic acid. Good on those? Oxyacids are only complicated because you have to remember the Oxy Anions. So for oxyacids, you're going to have a number of hydrogens. Again, we have hydrogens first, so we can identify it as an acid. And then that number of hydrogens is going to be equal to the negative charge on the oxy anion. So nitrate has a 1- charge, so it has 1 hydrogen. Sulfate, or sulfite, has a 2- charge, so it has 2 hydrogens. Sulfate also has a 2- charge, has 2 hydrogens, because each hydrogen ion has a 1+ charge. And then we even have one H3PO4, which is, well, PO4 3- is phosphate. So we have 2 different endings that we use for these. If our oxy anion ends with ITE, again, these say acid. So if the oxy anion ends with ITE, you change ITE suffix to OUS when it's the acid. For ATE, we change ATE to IC. There's a prefix, so if it's like per something acid, the prefix stays there. The only thing we change is the ending, and notice that there is not a hydro in front. So if you're trying to go from the name to the formula, if there's hydro in front, it's going to be a binary acid. If there's no hydro in front, and it still says acid at the end, it's going to be an oxyacid. It's a lot of rules to remember. So here are some of the oxyanions converted into their acid names. Nitrite ends with ITE, and its acid name is nitrous. So it goes OUS, but then nitrate, ATE, gets changed into IC. So definitely have this table or the Polyatomic Ion Study Guide at hand, along with these rules. I mean, these are, I'll print something out so you can have just like, these are all the like rules that you need to have. I'll put something together. And again, none of this nomenclature stuff is going to be on this exam, because chapters 1 through 4. This is not chapter 5. All right, so again, we have to identify what type of compound we're naming, even though that this says oxyacids. We have hydrogen first, so we know it's going to be an acid. And then we have nitrogen and oxygen, so it's going to be an oxyacid. So then when we name this, we just need to know what the name of that oxyacid is. Oops, sorry, NO2 minus. So NO2 minus is nitrite. So we're going to change this ITE ending to OUS, and it will be nitrous acid. So the hard part is knowing the names of the oxyanions. And then just remembering that ITE is OUS, AT is IC. So for our next one, again, starts with an H. It's an acid. And then we have chlorine and oxygen, so it's an oxyacid. And this is, oh, this is, I think he needs to chill. So chlorate here is ClO3 minus. So this has ClO4 minus. ClO4 minus. So that's one more oxygen than the base form. So this is going to be perchlorate. So perchlorate. So then when we name this, we leave the per, leave the chlor, and change the ATE to IC. This is perchloric acid. So every part of the name is giving you some piece of information that you need to write the formula. Any questions on oxyacids? Nope. Yeah.
You don't have to say, you don't have to put anything for hydrogen when you're naming these ones?
No, you don't. Do you know why? So the charge on the oxyanion is always the same. So just like when we're naming ionic compounds, the anions always have the same charge. Here's the same sort of thing. So if we just had this name, we would know that it's, well, perchloric, so we would know that it's perchlorate. And perchlorate always has a 1- charge. So if it has a 1- charge, that means that it's always going to have one hydrogen, because they've always got the same number of hydrogens as the charge. Yeah, good question though. So you don't need to say anything about how many hydrogens there are. Some good chill, because you can figure that out from the rest of the information. So this is the awesome flowchart. I don't remember how much gets cut off on this. So first, right, identify what the broad group is. If you have a metal, then it's ionic. If you have nonmetals only, aside from starting with hydrogen, then it's molecular. And then if you have hydrogen as the first element, it's an acid. Then for ionic compounds, so there's actually some examples here on the next one. Let's do carbon monoxide. All right, so carbon monoxide, we would say this has carbon and oxygen, so it's nonmetals only. Remember, metals are everything to the left of on this periodic table, the red zigzag line. So we'll name it using the molecular nomenclature rules. So we'll use a prefix, the name of the first element, a prefix, and the name of the second element. So in this case, we named this one before, but this would be carbon monoxide. You wouldn't say monocarbon monoxide. You would say dicarbon. So this is, yeah, where we leave ones off sometimes. Really most of the time. Yeah, so this is one of the things that I would print out, and I'll try to compile these things into like a couple pages, and then you can have those, print those out, and then just have them on hand when you're working on things. So if we had something like calcium with fluorine, then we would identify first that we have a metal as the first element, so it must be ionic. Calcium's all the way on the left side of the periodic table in group 2. And then we would say we have, well, move down the flow chart and ask, do we have a metal that forms only one type of ion, or is it a metal that forms more than one type of ion? So in this case, calcium's in group 2, which is one of the groups of elements, or groups of metals that form one type of ion. So we'd use the name of the cation, and then the base name of the anion plus IDE. So our name of the cation is calcium. And then it's just the base name of the anion with IDE, so fluoride. So if you want to get practicing on these right away, the nomenclature worksheet is on Canvas, and that's next week's lab. So you could start working on that now. If you wanted to. The last thing that we're going to cover for this chapter, though, is formula mass, which is the mass of a molecule or formula unit. Remember, ionic compounds are technically formula units, but you can think of them like molecules. So the formula mass for any compound is the sum of the atomic masses of all the atoms in its chemical formula. This is going to be a concept that we use for almost every problem for the rest of the semester. So if we wanted to, been using carbon dioxide a lot, say we want to know the formula mass of carbon dioxide. So we need the atomic masses of all the atoms in the chemical formula. The atomic masses are on the periodic table. So what we do is we say, okay, we have this, we have a carbon and oxygen, and then we'll go and look up, I'll use colons here instead. Carbon's atomic mass is 12.011. We haven't talked about moles yet, but this is in units of grams per mole. And we have one carbon atom. So we multiply carbon by 1. For oxygen, our formula mass is, or atomic mass is 15.9994. And it's also grams per mole. Atomic masses are all in grams per mole. But we have 2 of these, so we multiply it by 2. So we can do, all right, so 12 times 1, this 12.011, is going to be 12.011. And then plus 15.9994 times 2. That's 99988. For exams, I'll give you a periodic table with probably fewer significant figures on each of these than that, and that's the number of sig figs you should use. We'll use all of these here, though. So then we just add 31.99988 plus 12.011 for 44.01088 grams per mole. And then we would round this to 3 decimal places. So it'd be 44.011. So, right, this is the number of atoms, the first element, atomic mass of the first element. I guess I switched those. Number of atoms in the second element, atomic mass of the second element. And then you just keep going, that's what this ellipse means, until you've calculated the masses of all of the individual elements, and you can add those up. So the formula mass for CO2 then would be this. I got a couple more examples here too. So for the formula mass of dinitrogen monoxide, which is also laughing gas, right, N2O. So we have nitrogen, we have oxygen, we have the mass of oxygen, or nitrogen is 14.01. I'm going to use 14.01 grams per mole. And then we'll multiply that by the 2 nitrogen atoms. And then oxygen is, I'm just going to use 16.00 grams per mole. And there's only one of those. So then we'll get 14.01 times 2 is 28.02. And then this is just going to be 16.00 grams per mole. And we add those together. So, oh, interesting. It is 44.02. It's almost exactly the same as Carbon dioxide.